Quantum numbers are like electron address, providing a unique set of 4 numbers that describe its states or state within an atom. There are 4 quantum numbers. The first one is the principal quantum number. This number is like the city or main street where the electrons live. It tells us how far the electron is from the center of the atom or the nucleus. A bigger number means electron is further away and has more energy levels or has more energy. These are the energy levels starting from the nucleus. These circles here are the energy levels. And now these are the principal quantum number. N equals to 1 in this energy level. N is equals to 2 in this energy level. N is equals to 3 in this energy level. And N is equals to 4 in this energy level. We all know that electrons move from these energy levels, from the ground state to the excited state. So if you see the electron here, that means the electron is in ground state. It is in low energy level. But once it jumps to this next energy level, it is no longer in ground state. It is already in excited state because this energy level is higher than this one. The same thing with this energy level. So the further the electron from the nucleus, the higher the energy value or the energy increases. So it has more energy if the electron is in this position. Okay, a higher N value corresponds to a larger atomic radius and greater distance from the nucleus. Principal quantum number also have the main energy level. Aside from the energy level that I mentioned earlier, these are the main energy level. Electrons occupy specific shells or energy levels which are different by the principal quantum number. These are defined which are defined by the principal quantum number. Again, let me repeat that. Electrons occupy specific shells or energy levels which are defined by the principal quantum number. And what are the main energy levels? We have K, L, M, N, O, P, and so on and so forth. Each main energy levels can hold a maximum number of electrons. Like for K, it can hold 2 electrons. For L, it can hold 8 electrons. For M, 18. N is 32. O is 50. P is 72. Q is 98. And aside from the main energy level, it also has subshells. For each N, there are N possible subshells. We call that S, P, D, F. S stands for sharp, P stands for principal, D stands for diffuse, F stands for fundamental, with L values ranging from 0 to N minus 1. So if you have N equals to 1, it has 1 subshell, that is 1s. If N equals to 2, it has 2 subshells, which means it has 2s and 2p. And if N has 3, it has 3 subshells, which means it has 3s, 3p, and 3d. Then next we have the azimuthal quantum number, the second quantum number. This number is like the shape of the house on the street. It tells us the shape of the area where the electron can be found. The most common shapes are the S for a sphere, it's like a ball, where L equals to 0. The second one is the P for a dumbbell, like 2 balloons tied together. This is L equals to 1. And if you have D for a clover, it's like 4-leaf clover, L equals to 2. These are some sample images for the sample of common shapes. So for S subshell, this is the shape where L equals to 0. For P subshell, this is the shape where L equals to 1. For D subshell, L equals to 2, this is the shape. And then for F subshell, L equals to 3, this will be the shape of the subshell. How to determine the azimuthal quantum number? Note that the angular momentum or quantum number can be found from the principal quantum number n. Once the value of n is known, the values of L range from 0 to n minus 1. When n equals to 4, the values of L are 0, 1, 2, 3. So this is the table that can help you to determine the azimuthal quantum number. So if we have principal quantum number 1, the azimuthal quantum number is 0. If we have principal quantum number 2, the azimuthal quantum number is 0 and negative 1. If we have principal quantum number 3, the azimuthal quantum number is 0, 1, and 2. If you have 4, it's 0, 1, 2, and 3. If you have 5, you have 0, 1, 2, 3, and 4. If you have 6, you have 0, 1, 2, 3, 4, and 5. If you have 7, you have 0, 1, 2, 3, 4, 5, and 6. If you have azimuthal quantum number 0, that is the S subshell. You have 1, that is P subshell. 2, D subshell. 3 is F subshell. So example, when an electron resides in the 3P subshell, N equals to 3 and L equals to 1. Then example, N equals to 4, L equals to 2. That belongs to 4D subshell. The third quantum number is the magnetic quantum number, represented by the symbol ML. This is like the specific room or apartment inside the house. It tells us how the electron's house shape is tilted in space. So how to determine the magnetic quantum number? For L equals to 0, that is S orbital. ML can only be equal to 0. This means there is only one S orbital in any S subshell. But if L is equal to 1, that is the P orbital, ML can be negative 1, 0, positive 1. This indicates that there are 3 P orbitals in a P subshell. And then for L equals to 2, that's the D orbital. ML can be negative 2, negative 1, 0, positive 1, positive 2. This indicates that there are 5 orbitals in a D subshell. Okay, the last quantum number is the spin quantum number, represented by the symbol MS. This number is a special detail about the electron itself, like a person's favorite color. It indicates the electron spin, which can be up or down. So you have positive 1/2 for spin up, negative 1/2 for spin down. Say you have electron configuration of 1s1. The orbital notation is like this. So the spin quantum number is positive 1/2 spin up for first electron. And then if you have 1s2, the second electron, as you can see the orbital notation, the arrow is pointing downwards, so it's gonna be negative 1/2 spin down.